Yes, begin.
So I'll just share as well the link.
Okay. So Valeria has shared the link. Let me put this on the website of the event also, so that people here can see it. Not everyone is online. 1 minute, everyone.
Shall I start?
Yeah, you can start. I'm placing the link that you pasted on the website so everyone can download it. Let me tell them when it's ready. Okay, we can begin.
Great. Hello, guys. So I'm Valeria, and I'm a computational and data scientist at Pastor C. And today we will do training about analyzing time series. So before actually beginning the training, can you all please copy the notebook by logging to your Google account and by selecting the file and save a copy in Drive, and let me know when you do that. So I'll wait a couple of minutes. So is everyone ready?
Oh, Valeria, go ahead.
Great. So what is exactly a time series? So a time series, as the name suggests, is a sequence of several data points that are collected at consistent intervals over a set period of time. And for example, weather records such as temperature, humidity, maybe the heartbeats per minute, or the stock prices. And we will plot that as time is in the x-axis and the value measured is at y-axis. So for this training, our data set is sensor data collected every minute for 16 days and includes 5 time series signals such as humidity, temperature, light, carbon dioxide, and humidity ratio. And basically our goal, after analyzing and visualizing our data set, will be to perform a binary classification and to identify whether the room was empty or occupied based on the sensor data that we collected. So the first step is to clone the Git repository that contains the dataset. So in order to do that, we use !git space clone, and then you paste the website of the GitHub repository. So if you run that, it will start. Sorry. Let me restart the session. Okay. So now, hopefully it will, yes. So now the data set have been cloned and downloaded temporarily on our notebook. Then the second step, has everyone done that? Did it work for everyone? Yeah. Great. So the next step is to import the libraries that we would require to perform our task. And as Nico said earlier, in Python, we use import. And for example, here we import NumPy as NP. NumPy is a library used for manipulating matrices. Pandas is used for mainly data analysis, and Matplotlib and Seaborn are for data visualization. And from here, you can see that we are selecting from a specific module, let's say, to import specific functions. So scikit-learn and Keras TensorFlow are libraries or frameworks that are used for machine learning. And finally, we will import some libraries from stats models that we will use them to calculate some statistical measures. So if you click on the left or shift and enter, it will run. So now we are ready to start. And the next step is to actually read our dataset. So in order to do that, we will need the temporarily path of the dataset. And in order to identify the path, we click the file symbol on the left on toolbar. And now here we can see this is the dataset that has been cloned from the GitHub repository. So if you click on that and then click on the ML project and then the files, we can see the different files that are included in the repository. We are interested at the data CSV at the moment. So in order to identify the path, you hover at the dataset at the file of interest, and then you click on the 3 vertical dots, copy path. And for example, if you paste it, it's just the path. So in order to be able to use it, you would like to select the whole path and use single quotation marks. So now it becomes a string. And this is the same to the one here. So if you run that, so now we have our temporary path, and we can use the read CSV function from the pandas library to read our dataset. So now we have read the dataset. Has everyone done that? Is everyone on the same page? Yes, yes. So now we will start exploring our dataset. And an initial start would be just identify the shape of our dataset. So in order to do that, we can use, so we named our dataset as df. So we can use the print to print our shape using the shape function. So you specify df.shape. And if you print that, you can see that the result is 20,567. So in order, this is basically the number of rows and the number of columns of our dataset. And if you would like to extract the individual numbers, you can use the F shape and just use the index of the element that you would like to extract. So index 0 is rows and index 1 are the columns. And from here, we can also use a print function to just print the individual shapes. So as a following step, I think we would like to see our data set. So if we would like to see some of the top rows of our data frame, we can use the head function and we can quickly view our data set. Then default value is 5. So if you just run that, you can see just 5. But if you put, for example, 10, you can see the top 10 rows. And we can use the tail function to see the bottom rows of our data frame. Another useful function from pandas is info, and you can use the df, which is our data frame .info. And for example, here we can identify the number of columns, the name of the columns. We can see that we have a column with dates. This is our temperature, the time series, and here our last column, occupancy, is basically our target class. Additionally, we can identify whether there are any null elements or values in our data set. So our data set at the moment has none null, so it's okay. In the case that maybe some null values exist, we can use different methods to replace the missing values, or we can just remove them depending on our data set and our goal. And additionally, using the info function, we can identify the data type of our columns. And from here, we can see 3 different data types. So date is assigned as an object. Temperature, basically our time series signals are classified as float 64. And our occupancy, which is the target class 0 or 1, is classified as integer. And also we can see that we have that many rows as we previously seen at using the shape function. And we can get the range of our rows. So continue to the describe function, another very useful pandas function, and it is mainly used for numerical values. And from here, we can see count is basically the number of rows that exist for each column. As I said before, it is mainly for numerical data, so we can see here that the date which was assigned as an object doesn't appear. And we can see the mean, standard deviation, the minimum and the maximum, and the quartiles of our data set. So this is useful because, for example, we can get a glimpse of how our data set might look like. So for example, with temperature, we can see from that the mean is around 21 and the standard deviation is 1. So there are no big discrepancies between like the values of our temperature. But in comparison to light or carbon dioxide, we can see for light, for example, that the mean is at 130, but the standard deviation is 200. And we can see that from the minimum and maximum values that the range is quite large. So this might suggest, and it will be confirmed later on by visualizing the data, that maybe light and carbon dioxide might have some outliers, for example. So let's remind ourselves how our data looks like. So this is the date. These numbers here are the index. So it's the date, our time series data, and our target. So a useful thing to know is how many rows are associated with an empty room and how many rows are associated with an occupied room. And this can be done easily using the value counts function. So we specify here our data frame, and we select the occupancy column, and this can also can be written as df dot occupancy and value counts. So this is an alternative way to do that. So if we run just one of them, we can see the results, and if we run the other one, it's the same results. So from here we can see that like around 16,000 rows are associated with an empty room, and 4,750 rows are associated with an occupied room. This is a useful information in order to understand whether our dataset might be balanced or unbalanced. If it is a balanced dataset, then the two classes should roughly have the same number of rows. So our dataset is not balanced. And this is useful information to know when we will do our classification to select our metrics. So please, if you have any question, just ask me and let me know. So previously we have seen from the info function the data types. We can also identify for the specific column our data type, and as we've seen, date column is assigned with an object data type. However, we would like to convert the data type from object to date time in order to be able to actually use our date column as we should. And this is done by so here, because we would like to convert the same column, we give the existing column name, and we are using the to_datetime function. And here we specify again the column that we would like to convert to datetime. So if you run that and you use the dtype function, we can now see that the data type has been converted to datetime. And from here, we can extract several information since it's a datetime column now. So for example, here we can create a new column called weekday int, which is weekday integer basically. And we use the date column and we use the .dt.weekday function. That this function basically gets from this information that our weekday is 0, as you can see here, and basically 0 means Monday, 1 is Tuesday, and so on till Sunday, which is 6. So basically from just the date that we have, we can extract which weekday it is. So this date here is associated with Monday. So all these measures have been collected on a Monday. And just to make it like more visually easier for us, we can use the map function, and by creating a dictionary, so the weekday map is a dictionary that we can map the values that we have extracted before. And basically, as I said before, 0 is assigned to a Monday. So we create the dictionary and we create a new column, which is weekday categorical, and we assigned it to the weekday integer, so it's the same. And then we can map the dictionary, and from here we can see, so here is the tail, we see the last rows of our data frame, and from here we can see that now the date 18th of February was a Wednesday with number 2. So this is just useful information, just to have a better understanding of like when our data was collected. And we can do that not only for the weekdays, but also for the year, month, the specific day, hour, minute, and second. And this is done by using the datetime index function. So here we created all these new columns. And basically by using the datetime index and by assigning which information, let's say, you would like to extract, we can see that our data frame has been updated with more columns. And basically here, this is just extraction of all the information that are included in the date column. So the year 2015, month February, this is second day at 14:19 with 0 seconds. The seconds are 0 since our data was collected every minute. So now we have extracted the different columns. We can use other functions to identify, to understand our dataset even better. So for example, here we can identify the range of our dates, and basically by using the date column again and extracting DT, date, and minimum, and also the date maximum, we can identify that our data frame has data collected from 2nd of February 2015 till the 18th of February, so the 16 days that I mentioned earlier. And this is quite useful just to, like before visualizing the data set, just to get our head around like when our data has been collected, how our data looks like, and so on. So now we can use the date column. We can set our date column as an index, and by doing that, we can extract more information. So we are using the set index, And we can now see instead of 0, 1, 2, 3, and so on, in the index place is the date. So before continuing, we can use the drop function and just to drop the unnecessary columns that we have extracted. As I said before, our dataset has been collected in February 2015 for every minute. So there is no like point of having the year, the month, and the second columns. I mean, we could keep them and not use them, but just to see how the drop function works, we can basically specify the f.drop, and here you say which columns you would like to drop. So let's run that. And from here, we can see still we have the date as an index, and we cannot see the columns that we have dropped. And here, since our occupancy is our target class, I prefer personally to be at the as the last column. So here we use the reindex function just to basically to move the occupancy column at last. And now, since we have set the date as an index, we can use the log function. And basically here by using log, and if you specify, like, for example, the date that you would like to have the data set from. So here you will see it's basically a data frame with only the data from 13th of February 2015. So this is useful if you would like to have some analysis for the specific day. Or you can use them between time function, and you can specify like 2 times that you would like to have the data from. So here we can see that is all the days between 2 and 5. Again, this is useful if you would like to have to make an analysis for specific timings. Or you can use the add time function that you specify a specific time. So here we can see all the data points collected at 5:47. Again, this is useful just maybe to visualize, or if you would like to, if we had more data points, it might be useful just to know what was going on at that specific time. Additionally, another function useful for time series is resample, and basically it's a way to downsample your data into days. For example, if you say D, it's days, and if you say W is week. And by using the resample and using the size, we can identify that how many rows basically are associated with the specific date. And here, which row, how many rows are associated with the specific week. The resample, the weekly resample starts with a Sunday. So again, this is something useful for us to get an idea of how our data look like before actually visualizing it. And here we will create a new data frame called df mean per day. And basically we are using the resample of days, and we are selecting specific, like the specific columns that we would like. And this is the 5 time series. And here, instead of giving the size, identifying the size, how many rows, here we will calculate the mean of all these per day, of all the rows for each date. So we can see here that, for example, as we've seen here, like the 2nd of February has 581 rows, and this is the mean of those rows. And this is the same for everything. And so these will be used later on when we are plotting our data. So we've seen before the value counts function. It is basically similar to size counts, how many rows are associated with the specific, with the unique values. So in our weekday categorical column, we only have like the Monday, Tuesday, like the weekdays. So this is our unique elements. And with using value counts, we can identify that this number of rows are associated with a Monday. And we can identify that by using 3 different approaches. So this is a weekday CAD and value counts, and you can use, it will be the same if you use the weekday integer, but instead of Monday, Tuesday, it will be 0, 1, and so on. Our second approach is by using the index.dayname, and again, value counts, and the day name extracts basically again which weekdays. And again, we see similar results. And our last approach is again using index, but instead of day name, we use day of week, and again, value counts. And here we can see that the day of week is represented with integers. So if everyone is happy and has no questions, we can continue to our data visualization. Is everyone okay? Okay. So for the purpose of this training, we will use 5 different plots to visualize our data set. We will use a line plot, which is basically used to identify the behavior of our signal over time. We will use a box plot, which is basically used to represent groups of numerical data through their quartiles, as we've seen above, using the describe function, the 25th, like the median, 25th or 75th quartiles. Additionally, we will use a histogram, which is basically used to represent data in forms of some rectangles, which is basically counting how many times a specific value might appear, a specific range of values might appear in our dataset. We will use a heat map, which is used to show the magnitude of a phenomenon as scalar in 2 dimensions. And lastly, we will use a pair plot, which is used to plot multiple pairwise bivariate distributions in our dataset. So here, if we run that, so we are using a for loop and the seaborn line plot to visualize our 5 time series signals. So with the line plot, we specify our data set, our data, which is our data frame. And here you specify which column you would like to appear in the x-axis and which one at the y-axis. And here, since it's a for loop, we gave the name. So here we take each one, each signal. And from our plot, we can see that the blue line represents the original signal and the yellow line represents the mean, which is basically our new data frame that we just now created using the downsample, using the resample, function. And basically, again, we give as a data our new data frame. Again, X is our date, which is the index, and Y is our signals. And from here, we can see that at the x-axis is our date, and on the y-axis is basically the range of each of our signals. And we can see the different behaviors of each signal. So here we have temperature has for each day a high peak, it drops and again rises and so on. Another useful information to have for a time series signal is to identify whether it is a stationary or non-stationary. So as the name suggests, stationary means that our signal does not vary in time. So it's quite static, let's say, with small changes. And when we say non-stationary, our time series signal changes through time. And this can be identified by using a p-value and some statistical measures. And here we use the AD Fuller function from the stats model library. So here is our, so we created a function and we extract the information that are of interest for our training today. And to know if a signal is stationary, we need the p-value to be less than 0.05 and the test statistic to be less than critical value. So it's not really important what each one means at the moment. We just want to know, like, to identify whether our signal is stationary or not. So here we can run our function and we can see that our temperature, we know that our signal is stationary and we can see this from these values here, and our humidity is non-stationary. So for example, we've seen above that our temperature had very small standard deviation. So we can see that from that is quite steady. So it has more changes. And this can be seen from here as well, since it is suggested that our signal is stationary. Now, another useful metric for our, like to know, to visualize for our time series is autocorrelation, which basically, as the name suggests, is a correlation of the signal with its past values. So here we plot the ACF plot from the stats model again. And here is our temperature, which is quite steady. As we see, lags, you can put a different value. So you can use a bigger or like a larger or a smaller value. And from here, from the plot, basically, so when it's the correlation is coefficient is at 1, it means that it's the same. And here we can see that from the plot, we have like this second peak here, which is roughly around 1,300. And this basically for our temperature suggests that the signal is similar when at like the 1,300 points. And if you remember from our downsampling of the days before, we saw that our each day basically had roughly 1,000 something number of rows associated with each day. And this can be seen actually from here. And following that, and if we calculate the mean basically of this resampling, so the mean of all, like the number of rows, this is the mean number of rows for each date, like in average. So we can use that number for our next graph, which basically this graph, as you can see from here, we will identify. So this is our original. We will identify the trend, the season, and the residual. So what exactly means? Trend is basically our long-term direction of our time series. Seasonality is basically the periodic behavior of our time series. And basically here we will use, this is where the mean value that we calculated here will be used. And lastly, the residual is basically if you add the trend and the seasonality and you subtract them from our original time series, is basically the remaining of the time series, which is described as unsystematic and short-term fluctuations. And basically we can see here the trend of our temperature here is quite increasing, and then it drops again for these days, and again increases and drops. But we can see that the seasonality, like for every day, it has a peak. And so this is basically like the mean values that our period, which was calculated from here. And we can see the rest, like the remaining of the time series. Another like useful, so now these were mainly line plots. Now we will examine the box plots and histograms. So from this figure, even though that they are very different plots, we can actually show that they show similar information. So for a box plot, we use the seaborne box plot, and we just need to specify the X value, which in our case would be the temperature, humidity, basically our signal. And for a hist plot, we just need to specify again the column, and we can see the results if you run that, we can see. So this is temperature and temperature, and you can see from here the x-axis of the box plot and the x-axis of the histogram is the same. And you can see that the majority of the data points of temperature collected are around between like 20 to 21 degrees. And this can be seen from here as well. So basically, where the box moves is the same, where the majority of our data lies. For example, with light, we have like very large range, as we've seen from the describe, as we said, that the standard deviation is quite big and that we might experience of having some outliers for both light and carbon dioxide. And this is kind of confirmed here, that the majority of our range lies in those values, in those ranges, but we still have some other values that are out of the specific range, and these can be assigned as or assumed to be outliers. And you can use the histogram also to identify that. So we can see the majority are here, and the rest, we still have some values, but very, very few. And again, same thing for humidity ratio. Another useful plot is the heat map, which basically shows the correlations between our variables and their self as well. So we can use the seaborne heat map. You specify which columns you would like to have the correlation, and you specify here the .core function. So if we plot that, so from here we can see that the diagonal line is basically comparing the correlation of the temperature with itself, the humidity with itself, and so on. And from here we can see that, for example, light is highly correlated with the temperature, and we can also see, as expected, also the humidity ratio is highly associated with humidity. And here I also included the occupancy, which is the target class. And from here we can actually see something very interesting, that the light, our variable, our signal light, is very highly associated, correlated with our target class. So this might be very useful for our classification. So keep that in mind. And this is a very useful plot to just understand how your data is correlated. And here are some bar plots. And we can see, so this is the light. And probably this is the reason why it's very highly correlated with the occupancy. So with the bar plot, we gave as our data frame. We specify as X axis the weekday categorical column, and Y axis we can see here the light. And here is quite useful hue, which is basically identifies and gives a specific color to each class. And from here, we can see that when the room was empty, so class 0, the light was very low, but when the room was occupied, we can see very high values of light. And this is something that is quite descriptive for our data set and to understand that. So this is a bar plot for each weekday. Now let's see a bar plot for each specific day. So again, we specify the data frame, the column day, and here we see the humidity. And this is not like very informative. We can see that there is we can see that it's a bit larger, the humidity, when the room is occupied, but it's not very distinctive as the light, for example. And also we can see from here that on the day 7, 8, 14th and 15th, which is weekends, the room was always empty. Something that is useful to mention is that, so for example, here the bar plot calculates the mean of the humidity for each day. So if we had, for example, more months, it will be the mean of day 2 of all the months, basically. And here we can see, so we plotted weekday, we plotted the day, and now here we plot the hour column, and we can identify what happened between each hour. So here we see that from 0 till 6 o'clock in the morning, the room was empty. Then from 7 till 6 in the evening, the room was occupied. And again, from 7 till 11, the room was empty. And this is the carbon dioxide. And like in this hour is like the carbon dioxide is much higher than when the room is empty. And here, this is another way to see the box plots. The box plot above was basically for the whole signal, but here, like for the temperature or the humidity, but here we can identify the humidity ratio, for example, for each weekday and what happened for each of our target classes. And again, this is useful and it's similar to the bar plot, like visually. We can see that Monday humidity ratio, like most of like the means of the empty room are much smaller in comparison to the mean of the occupied room. We can see that for Monday, we have some outliers, but the main outcome, I think, from here is that the range basically of our humidity ratio is much lower than the range of when the humidity ratio when the room was occupied. And as a last plot, you see the pair plot, and basically here we select again which columns we would like to plot, and again here I used hue as occupancy. The diagonal lines are the temperature with itself. It's similar to a hist plot, but here is, instead of the temperature of as a whole, is the histogram for each target class. And here we can see, for example, that light with temperature can be used to distinguish the two classes, which is not that obvious, for example, with carbon dioxide and humidity. So again, this is something very useful to have and just get your head around of how your data might look like. So this is our final thing about data visualization. And if you don't have any questions, we can continue for our feature extraction and selection of our data set. Okay. So again, let's remind actually how our data looks like. So again, date is our index, our 5 time series signals, our new columns, and our target column. So for feature selection, we will use our 5 time series, our new column weekday with integer, and our hour column. So we won't use our day and minute columns. So here we can either select our data by just giving the columns of interest, or we can just drop the columns that we don't want. So this is the result will be the same. So as you have seen from our data visualization and from here, our signals have their own range. So for our machine learning models, it might, for some of them, it is required to have the features to have similar range. So it's easier for the model basically to actually identify which features are the most descriptive, not by just the maximum or minimum values. So here, if we just give this to the models, the model might assume that light and carbon dioxide are the most descriptive, since they are the largest values. Even though that for light might be this is the case, we don't really know, so we don't want to give this to our models. So we will use the min-max scaler from scikit-learn, and then the feed transform, where you feed the training data. And here, basically, what happens, it becomes an NumPy array, and we would like to make it a data frame again. So we use the pandas data frame function, and we specify the columns, the index, which is the same as our above data frame. So here now we can see that our signals have a range from 0 to 1, since we gave, this is the default range for max scaler. And now, since we've seen here in our data files that we also have a test.
Okay, can I ask a question?
Yes, sure.
Okay, I'm just seeing that you are trying to scale the data using the min-max scaler. So I was just thinking that, is there going to be an effect? For example, we can standardize using where we just subtract the mean and divide by the standard deviation, scaling by the standardization.
So basically, scikit-learn has different scalars that you can use, and this depends on your data, whether it is normally distributed, and if you would like your data to, like at the end after the scaling, to have like a normal distribution. And min-max scalar is like often used as the default one, which scales between 0 and 1. So of course, depending on different scalars, you can identify like the results might differ, but this is something else that we could examine. For example, which scalar is the best for our time series.
Okay, thank you.
Thank you. And so here we can see that we have a separate test data set that we could use. So we will read, again, this is the path of our test data set, and we need to perform all the same processes that we've done for our training. So we convert the date to have a data type. We create the new columns, we index, and here we select which that our data X test data frame is, and again we use the scalar that was introduced before for our test. And this is done separately because now the scaling of this is not like affected from the training values, but we use the same scalar. And now here we will just set our X train, X test, Y train, Y test. If, for example, our data set, we had one and we didn't have a separate test data set, we could use the train test split, which is a scikit-learn function. But for our case, is completely different. So we won't use that at the moment. And here we will build our models. So these are 5 models that are used for binary classification. For the scope of this training, I just left the default parameters. So let's run. So this is logistic regression, Gaussian naive Bayes, k-nearest neighbor, support vector machine, and decision tree. So now we have set our models, our estimators, and now we can use, we can plot the learning curve for those traditional models. And basically, these curves can be used to compare the different algorithms, or if you had different model parameters, you can identify how they affect the accuracy, and also we can use to determine the amount of data set used for our training. So we use cross-validation. Here now, this might take a couple of minutes, and we will see our results. And basically, the learning curve will show how the accuracy, like the behavior of the accuracy, for example, with the number of training examples. And as I said before, this is useful. For example, maybe your model can learn can be trained and learned and achieve the same accuracy with less training examples. So there is no need to use like all your data points, but let's see how our plots look like. Hopefully it won't take a lot of time. So please, if you do have any questions, let me know. So until the plots appear, we will also, oh, okay. So now we can see, for example, the logistic regression. So this is how many training examples were used to train our models. And we can see here that the training and here the cross-validation. So cross-validation is separating our data into different folds, and we keep a fold as a test, and then the model is trained on the rest. And we can see here that this is, we get very high accuracy from very few examples. This might be because of the light feature that is, sorry, very descriptive. And we can see here that the naive Bayes is compared to logistic regression doesn't achieve the same accuracy, and it's pretty steady. So with all the, as the model is trained with more data points, there is no actual change over time of the accuracy score. Here we can see there is some like increased inaccuracy. Again, support vector machine, there is no any change. And again, with decision tree, the cross-validation scores are not similar as to the training as in our other examples. So this is just a useful, like some useful plots that you can see the behavior of your model with increasing training data points. And since we're doing a time series analysis and classification, a useful deep learning model is long short-term memory model, which is basically used to, it uses input sequences into the model, and it predicts based on the important information from the sequence. And the model also identifies the not so many important information, and this is left out. So it uses only the most important. So here we just we will concatenate. We will just put together our X train and Y train and X test and Y test in order to use the our function. So this function is basically used to separate our data set into smaller sequences in order to be used as an input into the LSTM model. And here we create the sequences from our generated data function. And here we can see the shape of our sequence X sequence of our training shape data set, and this is the shape of our test data set. And here we just build our model. So this is Keras sequential. So sequential is a sequence, so it takes each addition into a sequence. So we give 50 hidden layers of the LSTM. We have dropout, and our activation is sigmoid. And since this is a binary classification, we will use the binary cross entropy, and the result would be some probabilities that we will convert to 0 and 1 here. So basically here we have set our estimators before, and here we feed our data set into our models. So this will take a few minutes for the long short-term memory. So basically here, the traditional models, we use the X train and Y train that we've created, and we predict the X test. And the long short-term memory model uses the new sequence data set that we just created. And from here, we can see the result is probabilities, and we convert this to 0 and 1, which 0 is that the room is empty, and 1 that the room was occupied. Okay, so now it's fitting. And we will use several valuation metrics. So now we still need the result, and we will use some so we will discuss about some evaluation metrics that are used for classification. So here, this is okay. So this is done. And let's talk about the our evaluation metrics. So as I said before, that matters with the fact whether our data set is balanced or unbalanced. So accuracy, basically, it's a metric that summarizes the performance of the model with the number of the correct predictions divided by the total number of predictions. And it's not very suitable for imbalanced classes. And we can also have the precision and recall and F1 score, where F1 score is can be used since the harmonic mean of precision and recall, it is used for imbalanced data sets. Additionally, confusion matrix is as the name suggests, is a matrix of n by n dimensions that is used to evaluate the performance of the model, and is defined by the number of target classes. And in our case, we have 2, which is empty or occupied. And from the matrix, we will learn when, like, we will see information regarding whether it is true empty or predicted empty, if it is true occupied or predicted occupied. And lastly, we can use the receiver operating characteristic curve, which is a plot that illustrates the ability of the diagnostic ability of the binary classifier system. And we could visualize also the area under curve, which is a value, and we can visualize it, and we will see it later on in our plots. It is important to mention that the area under the curve takes values that range from 0 to 1, so it will result between 0 and 1, where 1 means that the predictions are 100% correct. So the closer to 1 the area under the curve is, it means that the better our classifier has performed. So here we just print our accuracy score using the accuracy score function from the scikit-learn library. Also, we use F1 score, the precision score, and the recall score. And we have rounded using the round function up to 3 decimal places. And from here, we can see that for example, logistic regression, we basically, for all of our models, we have achieved very, very high accuracies. And one might say that this might be like overfitted, but we saw from our data visualization that by just using a light feature, we can identify whether it's quite descriptive, so we can identify whether the room was empty or occupied. Additionally, a different function from the scikit-learn library is the classification report. So here we can see again precision, recall, and F1 score, and also the accuracy. But the difference between this precision, recall, and F1 score with the above metrics is that this is the average between the two classes. But here it is the precision, recall, and F1 score for each of our class. So for our class 0, we have precision 1 with recall 97 and F1 score with 98. This is useful again to just understand, maybe if your data set is imbalanced, then you can identify which class might create a problem, and that might affect the other results. And from here we can see we give again the y-test and y-prediction of the logistic regression, and we can also use that for our LSTM model as well. And here we can see the confusion matrix of our logistic regression model. As previously seen, it is similar to a heat map. So we are using the Seaborn heat map. And here we can see that for logistic regression model identified 61.46% correct the class 0, and for class 1 the model has classified 36.4% correct the class 1. And here is, so the true value was 1, but the model predicted 0.08% that it was of class 0. And here the true was class 1, but it predicted 2.06% times that the class was 1. And we can see this, it is similar for the for the long short-term memory model, with very slightly different. Here, the prediction, the true was 1, but it predicted 0.53%, but it was class 0. And lastly, as I said before, our receiver curve, we use the ROC curve function from the scikit-learn library again, and we can use that for the LSTM model as well. And here, basically, we calculated the false positive rate and the true positive rate. And here is our plot. And as I said before, the area under curve, the closer to 1, it means that it's like the model has predicted correctly our classes. And from here, we can see that it's very sharp. So we have very few false positive rate. And again, this might be due to the light feature. And we can see here the different, so this is our baseline, and we can compare our different models. And you can identify each model with the color associated with it. So this is the end of the training. Please let me know if you have any question. Again, you can email me or you can email Stelios. And thank you very much for listening.
Yeah, any questions for her? No, very well
Hello.
explained, Valeria. Then go ahead.
Hello.
Hello.
So I just saw from the confusion message that you printed last that sometimes we have this scenario whereby the prediction for a given class is high and the prediction for another class is low. Is there a way in which we can correct from the machine learning model so that we have a model that's not going to be biased to a given class in terms of accuracy?
Yes, so here you can see for the F, so if it is unbalanced, we said that the accuracy is not that correct, let's say, to be used. So we will use F1 score, and we have an option here, the average, which can, if it is set to weighted, then the model and the F1 score will assume, it will do some calculations in order to make to take into consideration that our data set is unbalanced, and it will give us a much better, much representative outcome. So if you go, let's say, if you go to scikit-learn, so scikit-learn, F1 score, at the documentation, here the average, you can set it. So weighted, it finds the average weighted by each class, basically. The default one is binary, which assumes that the classes are balanced.
Okay, thank you. So I was thinking that is it maybe if we can go back and try to regularize this algorithm is going, I don't know if it's going to affect whether it's going the prediction in terms of the bias in terms of bias or not, because I'm just thinking that one of the key things that we do in machine learning is to regularize so that we can overfit, we can't underfit or overfit. So I don't know if that is going to solve the problem. I'm just thinking, I don't know.
I mean, with the overfit, or for example, you can make sure that when you do the cross validation and when you do when you shuffle the data set, so there are various ways that you can make sure that for each fold all the classes are included, so the model can be training using all the data available from all the classes. So I think this might be the solution to the problem, for example, for overfitting, because the model won't learn just from, let's say, the class with the majority of the data points. It will also have some data from the other class, so you can use shuffle, stratified cross validation.
If there's no more questions, then thank you, Valeria, for your session today.
Thank you.
And we have a lunch break now, and we meet in 1 hour. Let me see. Yeah, so 1:45. So please be on time so we could end on time as well. Thank you again, Valeria. Thank you, everyone. Let's meet later. Bye.